Hello viewers, myself Yashoda. In the last few videos, we tried to understand light reflection refraction chapter. In this chapter, many books what I felt is that they given directly when you have the convex mirror. Yeah, so you have the convex mirror like this. Sorry, convex lens or concave lens. You studied very well. So in case of convex lens, what will happen when a light rays will passes, they are going to converge. Or in case of convex lens, concave lens, what will happen when the light rays form, they are going to diverge. But the reason why they are going to diverge and why they are going to converge, nobody are explained. Okay, let us in this class we'll try to understand why in case of convex, okay, in case of convex lens they're trying to going to converge, and why in case of concave lens they're going to diverge. So reason for this you're going to understand now. To understand this reason you need to know first of all what is in case of prism. Apex means the peak point of a prism we call apex, and the base, okay, which we going to hold the prism that we call as a base. If you take in laboratory you have like triangular object like three-dimensional triangle. In that the three sides also looking like base, but how you identify as a base? Base has some little rough surface compared to other two edges, so like that we're going to identify the base. So however, apex and the base, when you pass the light, okay, when you're going to pass light parallel to the base, what will happen? It will going to bend towards the base. Light ray will bend towards the base. Okay, this is rule you need to understand here. When a light ray passes to the base, okay, parallelly you're going to pass light ray to the prism, what will happen? It will going to bend towards the base. So now you are going to understand in case of lenses how the lenses are made up of actually. So you're going to understand how this made up of. Okay, now see the convex lens is almost looking like this, right? This is a convex lens. Yeah, so you're going to take the convex lens. It is a combination inside and again one prism. Again you're going to cut this lens into number of pieces. You can take the top layers will be like a prisms. Okay, base is more, top is less, like this prisms, and down layers are made up of inverted prisms. Okay, down layers are made up of inverted prism. Now you understand in the first slide, clear children, what you understand in the first slide, that the light ray passes parallelly, what will happen? It will bend towards the base. So now you observe in this figure, when you pass the light ray in this prism, top one, you take it as a prism. So when a light ray will passes through this, what will happen? It will bend towards the prism. When the light ray, this is at inverted prism. When light ray passes parallelly, what will happen? It will bend towards the mirror. So you can say observe here, and similarly second prism, you will pass like this, it will bend towards the mirror. Again this is also, when you pass light ray, it will also bend towards the prism. So center one, it is a rectangular glass slab, it will won't bend, it will go like this. So you can observe now all the rays will going to meet at some point. You're going to extend this rays, they're going to meet. This is why the lens, convex lens, going to converge. Understood children? The convex lens, it is a plus lens. The top, both the base are, what will happen? Both the bases, the top and down, we consider like a two prism, their bases will be meet. That is why the lens, the rays will going to converge. So we can call this as a plus lens. What will happen? The rays will come and converge. So what happen? Intensity, suppose this is intensity I1, this will have intensity I2, both will meet. What happen? Total intensity becomes I1 plus I2. So we're going to add your intensity. That is why we call convex lens as a plus lens. Okay, so that is why the rays will going to converge. And in case of concave, okay, what you observe, no, concave, you can go see the concave, how the prisms will be like inverted form, and this prism is rectangle small here, and again down one you can see the like this. So when you pass light ray, it is an inverted prism. What happened? It will bend towards the base. Again here also, when you pass a light ray parallel, it will bend towards the base. So you can see now this will go this side and this will go this side. So both are diverged. Intensity which will go, it is going to split. So we can take it as a minus lens. Whatever intensity is there, that will going to splitting outward. It is not combining like this. So that is the reason that it is the bases are opposite end. So it is not adding. So apexes are meted, bases and opposite. So what happened when light ray coming parallel to the base? It will go towards the base. Here also it will go towards the base. So that is the reason. Okay, so you clear, I hope now. Why concave? Convex lens, the ray will going to converge in convex. In case of concave, it will going to diverge. Okay, many books they not given. Please try to understand this point. And what is plane? Whose plane surface? In case of plane surface, they will go like this. They're going to not going to bend. They will go passes as it is. Okay, this is why the lenses, you can observe now lenses clearly. Concave and convex lenses. This is a concave lens. Okay, this is just a second, children. Yeah, this is concave. Concave. You can observe here, just imagine like a triangle. Again, with a downwards. It is almost, it is like a downwards, and here rectangular glass slab. Again, in the up portion, they're going to increase in triangles like this. Okay, just going to imagine like this. Or else you imagine one triangle and the top one more triangle. So when you pass light ray, it will diverge. Okay, diverge outward. When you pass in this condition, you observe like this triangles are, both the bases are meet. Okay, like this. When you pass light rays, they're going to converge towards the base, it will move. When you pass light ray, it will converge towards the base, it will go straight. So all rays will move, it will going to get the image. Clear, children? Regarding the lenses, how they're going to converge and why they're going to diverge. This is what we call converging and diverging lens, are also called minus lens and the plus lens. Okay. Now, important thing is to understand the ray diagram. To draw the ray diagrams, one thing you need to know first of all, what is the sign convention? While solving a problems also, this is important for PU board and also 10th board. They will give many problems, application level problems, they will give on the lenses. That time you must know regarding the sign conventions. Okay, you know very well concept, but you don't know how to take the sign plus or minus, you'll do mistake also, you're going to lose the marks. Okay, so that's why sign conventions are important. Let us see, in case of plane mirror, we already learned the sign conventions, right children? In case of plane mirror, spherical mirrors, in the last video we done the sign convention. If you have doubt, please go there and watch. And now coming to the lenses. So just whenever we're going to learn new thing, please compare that with the previous one and you learn, then you never forget. If you learn like a new topic, this will be very difficult for you to remember. So try to understand difference between mirrors and the lenses. See, focal length, coming to the focal length, in case of mirrors, what we take, and focal length, see, mirror is like this, no? Focal length, if suppose you're going to extend like this, focal length will present in before, okay, in front face only. So what we call this one, the focal length, always we're going to take from the pole to left side, it will be negative. So it is like, imagine like a positive axis, negative axis, opposite side negative, down also negative. So like this only. So focal length for concave mirrors. Okay, concave mirror, it will be inverse. If you take convex mirror, okay, convex mirror where outside is reflecting, no, you just imagine like this sphere, the focal is present positive side. In case of concave, negative side. Right children, it is positive. And convex lens mirror, it will be focal length is positive for concave mirror and negative for convex mirrors. And in case of lenses also, for converging lenses, you know, no, this is convex, is a converging lenses is positive and focal length is negative for diverging lens. Diverging lens is this one. So diverging lens it is negative. And object distance, what we call as a U, object distance, at what distance you place the object here. So object distance, what we call the D naught, or we can represent U. So object distance in front of the mirror for real object, and for virtual means when image in the last condition, when object is from behind the mirror, that condition we're going to take object distance as a negative. In case of lenses means, if the object is left of the mirror, okay, this left side and right side, suppose you consider, if you take left side, okay, object will take left of the lens, or if a real object, okay, in case of real object or left, what we take it as a positive. If object is the right side of the lens or virtual object, that time we can take it as a positive. Yes. Yeah, let us see. Last one. For image distance, you can take, see here, image distance. When it is real images will form in front of the mirror. sorry, in front of the lens. This is a real image. In that condition, we can take, see, along the direction of incident ray, we always take it as a positive. We need to take distances opposite direction of incident ray, what we call it as a negative. Same in case of lenses and the mirrors also. So if object is here, up here to here, we're going in the along the distance from optic center to the image we're going to take, that is as a positive we can take, and if go opposite side it will take as a negative. And focal length also you can see here negative focal length back side, okay, for diverging lens. And the magnification, you can solve this one using the formula, we can solve this here. So by using sign convention, you can see the picture clearly. This is for concave convex mirror, and for the concave mirror, yeah, for a convex and concave mirrors, in case of convex mirror, you can see if you go back, whatever, this is constant for both the mirrors. That is along the direction of incident ray positive, opposite to the direction of incident ray we need to take a distance is negative. Here also positive and negative. And here you can observe F1 and F2. You can just imagine this like a sphere, okay, where the center of curvature of the first will be present here. Okay, focus will be present this side. So that is why it is positive we're going to consider. Focal length. Here you're going to see the first surface where you kept it is like a sphere will come this side. So where any focal length will present left side. So it will present this side, no? So we're going to take it as a negative focal length. And here it is, because this side it is the positive focal length. And image will form in case of this one, you will get a real, okay, as well as virtual also. If you place the object very near, that time you will get the virtual image in this side, or else in all the other than all this condition you will get image in the opposite side only. So that is virtual and inverted image you will going to get. For that, what will take, image distance will be positive, because opposite side image distance will indicate as a positive, and object distance, object will always stand in front, no? So it is negative. Here also object distance is negative, image distance will be, image here in case of convex concave mirror, image will also form same side only, image going to form, so that image distance also be also negative we going to take here. This is about the sign convention. Let us see some ray diagrams or ray rules to understand this. See what is the ray rules are in case of like mirrors, as same as here also. When a light ray passes parallel to the principal axis, this is the principal axis here. This is a F1 is the center of curvature for this side, and this is a F2 is the center of curvature for this side. F1 and F2. Okay, focuses for this side and this side, and center of curvature somewhere here. Oh, when it is passes parallel, it is passing optic center, we call it as a O. F1 is a focus for first phase and F2 is a focus for second phase. So it is parallel to the principal, any light ray which is passes parallel to the principal axis. So after reflection, it will diverge, it will go outward direction. And but if it appears to coming from where, it appears to coming from focus. So remember, always infinity leads the focus, or if it is at focus, it leads to infinity. So in case of mirrors as well as lenses. So in case of convex, it appears to come. In case of concave means it will really form. Okay, passes through the principal focus. When it is coming from, appears to coming from focus, no? It will passes parallel to the principal axis. It is passing through the optic center, no? Without any deviation. It will go along the same path. Along the same path it will go after refraction. Clear, children, regarding concave lenses. Okay, let us see ray diagram same in case of concave also. In case of concave also same thing will happen. It will coming parallel, after reflection it will pass. This is the real, because actually light is passing. But previous condition we are going to extended, okay, extended ray is meeting, no? So that is virtual. This is really it is meeting. And here also it will when it is passing through the focus, it will after refraction it will go through the focus, and it will go up to the optic center. It will go as it is without any deviation. It will be same for both. Okay, let us to learn the ray diagrams. First, you need to know this table. If you clear with this table, then you can easily write the ray diagram. Sit out, like, try to learn this table. When you place object at infinity, where you will get image at focus, you will get. Okay, when or else when object is at focus, you will get image at. So this and this are related. Okay, children, this and this are related, or vice versa. They are. Okay. And then that time when object is at forms at focus, no, it is highly diminished on point side. It is real and inverted in case of convex. This is for convex mirror. Remember, for convex mirror like this, when you pass light rays infinitely, they will form at focus. We'll see ray diagrams. And when you place object behind 2f, that means beyond center of curvature, you're calling in lenses. In lenses, here calling beyond center of curvature, but here we call beyond 2f. It will form between 2 and f. It is diminished and real. When you place at 2f, image also at 2f only, at 2f2 here, same size, real and inverted. Between f1 and f2, it will form enlarged. So like this, try to understand. We already write this, I think. Yeah, try to understand 1 minute. I need to tell one thing. See, if you take convex mirror, how in case of concave lens, it will behave like a same as concave lens. Try to remember these two are similar. Here, when you pass the rays from infinity, okay, when you pass the rays from infinity, they're going to meet at focus. They're going to meet at focus here. But here, when the rays are coming from infinity, where they're going to meet, they also meeting at the focus in front. Here it is opposite end, that's all, because it is a lens, now it will form. So similarly, how the rules for the same rules will follow here. When object is at infinity, image will be formed at focus. Here we take in focus as f1 and f2, no? So it will form at f2. Okay, here it will going to form. When object is between C and F, C means we're going to take instead here, we're going to take F optic for center, and we're going to take center of curvature. Here we're going to take optic center O. C means here we're going to take 2f1, and this side we extend, we can 2f2. This is what we're going to take here and here. Differences. When object is at infinity, image at focus. When object is at focus, image at infinity, vice versa. Similarly here also. When object is at focus, when object is at focus, image will be formed at infinitely enlarged. Same rules for this and this also. And when you place object between, okay, when you place object exactly at 2f1, image will be formed exactly at 2f2. Like when you place object at C, image is also formed at C only, no? The same size, that is the rules. When you place object between C and F, here you are going to place object, then image will get a bit behind C. That means behind this side you will get image that will enlarge size. Suppose you will take object behind C like this, you will get image at between C and F like this with a smaller size. When you place object at between optic center and focus, that time you will get image in the same side. That is, this is what a virtual actually. This is a virtual image. These are our objects. This is only image will form same side with enlarged size. As it is, when you place object here, no, it will form opposite end with enlarged like this. So when you learn concave lens, please compare that with the not lens children. This is mirror. Concave mirror is same as a convex lens. All the properties. That means it will form same side here. It will form opposite side like this. And one thing which is from opposite side here, it will form same side. Okay, this is what the differences of this and this. Please learn comparatively, then you don't forget. Okay, these are the ray rules of the convex lens. Okay, convex lens you observe when object at infinity. You're going to observe here, my children. When you take an object at infinity like this, your infinite object, when you see image will be formed at f2. When you take an object between f and f2, okay, behind f1, so very far from the lens, so image will form between C and F. It will form, it is inverted form of the diminished size. It will form here point size. We're going to observe point size object. It is also real and inverted. Here also real and inverted, but diminished size or small and in size. Here when object is at 2, image is also formed at 2f2 of the same size. It will form real and inverted as well. And here when you take object between this 2f and f2, image will form behind C, that is enlarged. Now you can see enlarged real and inverted image. And here when you take at the focus image, see the two lines are never meeting, they are meet at infinity. So real and inverted, they meet at infinity. Now last condition, when you take very close to the lens, that time image will be formed at the same side, that is good extended rays, reflected rays appears to meet at them. So it is a virtual and erect image and enlarged. This is the last condition. Okay, this is about the lenses or ray diagrams. In case of convex, you observe convex is similar to your, okay, this is similar to your concave. This is concave lens. This is almost similar in case of convex lens. In case of convex lens, you learn, children, when you place object at infinity, image will be formed, appears to form at where? It will be appears to form because it will go like this. This is also diverge, but it will appears to meet at here. So in case of lens, when the object is at infinity, image formed at focus. And when you place object anywhere between infinity to the pole, where you will get image will get between pole and focus, you will get image with a diminished size. Similarly here also, in case of lenses also, when you take object at infinity, image you see appears to form at focus. And when you take object, okay, see it is the same side it is forming, no? So it is virtual and erect image and point size image will form. And in the second condition, between infinity, okay, when you take between infinity and the optic center O you're going to take, you will get the image in the same side. See, appears to meet, no, this appears to meet, so it is not really meeting. So virtual erect in the smaller size you're going to get, or you can write diminished size. Okay children, this is about the ray diagrams of concave and convex mirrors, sorry, lenses. Yes, ma'am. So, after understanding how to draw the ray diagrams, so to solve the problems, you must know the lens formula. In case of mirror formula, what is a mirror formula, children? You have remembered mirror formula? Mirror formula is 1 by V plus 1 by U. That will be is equals to your focal length, or it will be is equals to 2 by radius of curvature. This is the formula you learned. Okay, here this is a formula you learned. Okay, leave it this one. Remember this up to here. Okay, this is a mirror formula. Similarly, in case of lenses also, for spherical lens, what is the formula? It is minus 1 by u come. Okay, 1 by f, 1 by v and minus 1 by u. So how this derivation will come for a mirror, I already derived in one video. Please want to check, you just check what is the relation for r is equals to d of this relation, and this derivation too are derived and shown. And this is also I will do in the next videos how to derive this lens formula, will derive and show. And for namesake, now do you remember what is a lens formula? It will give the relation between object distance, image distance, focal length. Okay, and the radius of curvature, if you want, you can find from this. Okay, these are the relations given by spherical mirrors, the lens formula for spherical mirrors. And magnification. See, in case of lenses, you will get magnification is height of object by height of image, that is equals to minus v by u. This is for mirrors, please don't confuse, this is for mirrors. In case of lenses, you have object distance, image distance, sorry, I think wrong, image by object always will take, that is output by input. Remember, output by input always, whatever efficiency. Here magnification is our efficiency, that is output by input. Here also magnification is given by how much image you will get by object side, that is times we are going to magnify. So this is a magnifying, sorry, formula for magnification. And similarly, magnification is also related as object distance by image distance. Suppose you will take one lens, okay, where you kept object at 2f, okay, 2f when you place, you will get image at 2f2, okay, inverted image. So here you will take object distance as, let us take 2, image distance, what we are going to take, image height minus 2 we are going to, because it's down, no? So you have to consider minus. And object distance, it is an incident ray will go like this. It is opposite of incident ray, we are going to take from optic center to the tail. So we have to take in that time minus u we are going to take. And image distance, you can see the same direction of incident ray. So it is plus v will come. Image distance from optic center we need to take. From optic center to this you are going to take. So here magnification for lenses, it is plus v by u. Remember this formula while solving problem. This is very important. Magnification formula for lenses and for the mirrors. For mirrors it is, see, remember, mirrors and object, height of image by height of object is it. Only difference, mirrors means minus will come. Okay, mirrors remember minus sign. Lenses no minus, it is plus v by u. Okay, this is what the formula for Mirrors and lens. Definitely we'll solve the NCERT problem. That time you'll be clear with this topic. Yeah. In this chapter, the last concept but not least, they will definitely ask problems on this concept. What is the power of lens? So I think you have wearing the spectacles. When you go for spectacles shop, they will ask what is your power of a left eye, power of a right eye. Like they will write a LD or RD. So they will write LDR 2.2. This is as 2.5. Like that, they will issue one certificate. What is your left eye power and right eye power? So this is the power of a lens. How they are going to decide? This is a diopter, using diopter. So what is the power of a lens? It is a reciprocal of the focal length. Okay, power of a lens is reciprocal of focal length. Our focal length is equals to 1 by power we going to take. Clear children, what is the power of a lens? It is a reciprocal of focal length, or it is a focal length is 1 by power. So it is SI unit of power is diopter. It is represented with capital D, diopter. So diopter is the power of lens whose focal length is 1 meter. So then we call it as a 1 diopter. Let us substitute here. What will happen? Diopter you want. So power is equals to 1 by F. You place in place of F you substitute 1. What will happen? It will 1 diopter will happen. Okay, the power of convex lens. Convex lens, you know, this is a convex lens. In the convex lens, you take the power is positive, and for the concave lens, okay, this is a concave lens. For concave lens, the power will be negative. Okay, negative for concave lens and positive for convex lens. This is about the power and how to solve problems, and how to use this power when you give a two or more combination of the lenses, combination of the different kinds of the lenses when they going to adjust it. Okay, everything we're going to learn in the next coming videos. Okay, thanks for watching and keep watching. We're going to solve all NCERT questions regarding this light reflection and refraction chapter. Okay, children. Thank you, everyone. Have a nice day. Keep watching.